Hey, what's up? What is going on with the ith root of I? Why does e and pi and all this stuff show up? Well, honestly, at this point, I would be more impressed if e and pi didn't show up, but let's go over it anyway, because it's a lot of fun. So here we have complex logarithm equals this stuff. So if we look at complex exponentiation, this is the inverse, right? And then we have e to the z is e to the x plus iy. So the real part determines the magnitude of e to the z, and the imaginary part determines the angle of e to the z. So it kind of makes sense in a way that for the inverse function, or inverse multi-valued function, whatever, we would have that the real part would be a magnitude of sorts, and the imaginary part would be an angle of sorts, where arg z is the angle of z, but maybe it would be more accurate actually to say an angle of z, so sort of like 180 degrees and 540 degrees are the same sort of positionally, sort of like if you flipped on a snowboard, you would land in the same position doing a 180 or a 540. Anyway, let's start ahead. So we have the ith root of I, which is going to be I to the 1 over I. Ith root is the same as taking to the power of 1 over that root. And this is going to be I to the power of negative I. So if you multiply this by I over I and simplify, you will get I to the power of negative I. Multiplying by I is 90 degrees counterclockwise rotation. Multiplying by 1 over I or negative I is 90 degrees clockwise rotation. Now we could go ahead and do e to the log I to the negative I, because e and log will cancel out because they're inverses, which would just give us this thing back. And then we can go ahead and bring this power negative I down to the front of the log. So we have e to the negative I log I. And now we have e to the negative I. What is log I? Well, log I is going to be log magnitude I. So we have log of the magnitude of I plus I times the argument of I. So I times the argument of I, or an argument. Okay, so log, what is the absolute value of I? Well, it's 1. The magnitude of I is 1, right? If you start at the origin, you go 1 up to get to I, so that length is 1. So that's just going to be log 1, which is 0, so this part just goes away. Negative I times I, you might have heard of it, it's called negative 1, which is also just 1. So the negative I and the I are going to cancel out. We just end up with e to the argument of I. I keep saying the, but it's easy to say the. So what is this? So the argument of I is going to be the angle of I, so 90 degrees. But we want radians, so it's going to be pi over 2. But if you added 2 pi to that, you would get back to the same position. Add another 2 pi, get back to the same position. If you started at pi over 2, subtracted 2 pi, you would get back to the same position. So what we really want is e to the pi over 2 plus any integer multiple of 2 pi. And these are going to be all of our values of this thing. The thing is, complex exponentiation is not one-to-one. Sometimes different inputs can lead to the same output, which means when you inverse that, you can have the same input leading to different outputs. Well, that's not a function, but it's what we would call a multi-valued function. So complex logarithm is multi-valued, but we like to just pick out a single value. Of course, our human brains kind of like that sort of thing. So let's go ahead and choose k equals 0, and we're going to get equals e to the pi over 2, dividing by 2, and the exponent is the same thing as taking the square root, so we just get the square root of e to the pi, which I got to admit is totally beautiful. So this and this with k equals 0, wonderful stuff. Thanks for watching. Goodbye.